Welcome to the Space Gas training video. In this tutorial, we will guide you through the newly introduced nonlinear restraints, which are the latest features in Space Gas 14.2. In previous versions, node restraints in Space Gas were limited to whether a node was fixed, free, or attached to a linear spring in each of 6 degrees of freedom. Version 14.2 introduces 4 new types of restraints, as displayed on the screen: plastic restraints, friction restraints, variable spring restraints, and one-way restraints. In this video, we will provide a brief overview of each new restraint type. Let's examine a cantilever as displayed on the screen. We will use this cantilever as a benchmark to observe the impact of each type of the new restraints on this structure. Although there are 6 degrees of freedom, 3 in translations, x, y, and z, and 3 in rotations about the x, y, and z axes, we will apply the restraint exclusively to the y-axis translation to demonstrate how the restraints function. Nevertheless, the procedure and concept remain largely the same if you wish to apply the restraints to other degrees of freedom. The top beam is a cantilever which lacks any support at the free end on the right. The second beam is similar to the top one, except that it has support only in the y-axis direction. Let's observe how these beams respond to the 2 load cases. As expected, their behavior aligns with predictions. The support holds the right end of the second beam in a fixed position along the y-axis. A vertical reaction occurs at the right support of the second beam. Next, let me introduce the one-way restraint support. As the name implies, a one-way restraint supports a node in only one direction. For the right support of the third beam, let's set a vertical y-axis one-way restraint. Simply double-click it, and a node properties form will appear. By default, a node is free in space, meaning all 6 degrees of freedom are assigned a restraint code, denoted by the character R for each of them. The first 3 characters correspond to translations in x, y, and z, while the last 3 are related to rotations about x, y, and z. To fix the y-axis translation, change the second character to the letter F. This action instructs the program that we want this node to be fixed in y-axis translation. However, since we also require a one-way restraint, where the right end of the beam can't be pushed down but is free to lift up, we need to specify the support direction. Hovering the mouse over the form will display a tooltip, eliminating the need to remember these details. Since the right end of the beam can't deflect downward, there will be an upward reaction. This reaction direction essentially defines the support's direction. In this case, we require an upward restraint, representing the positive direction. As expected, under the first load case where the load points downward, the right end of the beam cannot deflect, resulting in a vertical reaction. However, under the second load case, where the load is directed upward, the node is free to move, and consequently, there is no vertical reaction. This essentially demonstrates how to set up the one-way node restraints in space gas. In the next part of the video, we will demonstrate how to set up a one-way node spring restraint. It is actually quite straightforward. Similar to the one-way restraint in the previous case, instead of completely fixing the node to prevent downward movement, which is denoted by the character F, we will now assign the character S to it, indicating the spring, and we will also assign the stiffness to the spring. Please note that the direction of the spring works exactly the same as in the one-way restraint that we have just demonstrated. Similarly, when a point load is directed upward, the spring has no effect on the node. However, when the load is directed downward, the spring provides some support, although it is not as stiff as a fully fixed support. One-way spring support is highly valuable in numerous scenarios. For instance, when modeling the elastic support provided by soil beneath a slab on the ground. The soil offers elastic compression support when the slab presses down on it, but it does not provide any tensile support when the slab is lifted upward. Not only can we assign a one-way spring support to a node, but we can also assign variable stiffness to the spring. To assign variable stiffness to a spring, instead of using the character S, which stands for spring, we now use V to represent variable stiffness. Then, we can straightforwardly assign variable stiffness values to the spring. This feature is typically useful for modeling embedded piles in soil, where the elastic support from the soil can vary depending on the movement of the piles against the soil. If we want to assign a plastic restraint to the node instead, it is also very simple and straightforward. A plastic restraint is denoted by the character P, which stands for plastic, and then we can easily set the plastic limit for the restraint. How the plastic restraint works is that if the reaction exceeds the limit, the reaction is constrained to the limit, and node movement may occur. Conversely, if the reaction doesn't exceed the limit, no movement is generated. Finally, in the last part of this video, let's explore the friction restraint type. In this 2D frame model, the base of the right column is assumed to have a friction restraint type. This means it is supported vertically along the y-axis but can slide along the x-axis. It's also quite straightforward. Firstly, we need to assign a fixed type support along the y-axis translation by using the character F for the y-axis translation degree of freedom. Next, we assign the character N, which informs the program that this is a friction restraint type for the x-axis translation. We must also specify the normal axis to the plane on which the column base slides. In this case, the column slides on the xz plane, so the normal direction is along the y-axis. Friction restraints are treated in a manner similar to plastic restraints, with the key difference being that their limit is a proportion of their normal reaction rather than a fixed value. Users can adjust this proportion value as needed. After analysing the model, let's quickly look at the deflection of the column base. We can clearly observe that the column can slide along the x-axis within the xz plane, just as expected. In this video, we have provided a brief demonstration of some of the new features in SpaceGASS version 14.2. This marks the conclusion of the video. Thank you for watching.